Modern quantum error correction tensor networks map millions of interacting qubits. Maintaining stability requires a continuous exchange of data across the entire graph. Inside these architectures, physical flaws can emerge. The most critical vulnerability is a topological bottleneck, a structural point in the network that devolves into a zero entanglement boundary, cutting off communication pathways. Locating these flaws is the purpose of the Tensor Network Quantum Gravity, or TNQG Diagnostics Suite. It operates as a local first engine designed to isolate these dead zones. Its primary function is evaluating massive network geometries to mathematically prove where these zero entanglement bottlenecks exist. Once a bottleneck is located, the suite can generate a mathematically verified blueprint to physically repair the broken circuit using an agentic AI router. We will trace the life cycle of a single diagnostic batch request, from the initial API payload to the final structural remediation. Processing this volume of physical simulation requires an architecture that isolates the back-end computation. Scaling diagnostics requires software that prevents heavy resource demands from stalling the host system. The lifecycle begins with a post request to the batch diagnostics API endpoint. The engine maps the tensor nodes on grid, preserving metadata like spatial coordinates. The payload connects the nodes with physical bonds. The critical parameter here is chi-e, defining the bond dimension. The engine resolves parallel bonds by multiplying dimensions and adding capacities, merging them while pruning recursive self-loops. With the physics input structured, the server must then manage the computational load required to process it. The operational configuration for this system requires that Uvicorn API workers are capped at exactly 1. This is because the application manages its own process pool executor internally to handle scaling. This executor utilizes native OS pipes to scale concurrent worker processes exactly to the host machine's total CPU cores, -1. This process isolation ensures that the background mathematical operations cannot block or crash the primary web server event loop. Calculating these graph topologies is compute-intensive, requiring real-time telemetry delivered over a WebSocket connection. Because calculations can take minutes, the server sends frequent heartbeat frames to prevent corporate proxies from dropping the connection during heavy math operations. If the connection lags, a backpressure mechanism drops intermediate data frames to ensure the final terminal state is delivered. Network issues are manageable, but the system must also account for the threat of a pathological quantum graph triggering an unbreakable sea-level math deadlock. To prevent freezes, the zombie process annihilation protocol triggers a SIG kill if a process exceeds 300 seconds, terminating the child process while keeping the parent active. If a worker exceeds memory limits, the Linux OOM sniper destroys it, throwing an EOF error. The suite traps this error, routing a failure message to the UI, preventing an event loop crash. These OS-level failsafes ensure the host CPUs are not locked into a permanent deadlock by unsolvable simulations. Once the computation is complete, the job reaches a terminal state, and the batch results array is delivered. The QEC metrics block evaluates subsystem integrity. The critical value is minimal cut capacity, representing the absolute maximum flow crossing the boundary. A failure is confirmed when capacity evaluates to 0.0, mathematically confirming the subsystem is topologically isolated from the rest of the network. This isolation identifies the location of a zero entanglement bottleneck. We can further assess the internal structure of the subsystem by looking at the logical routing depth. A routing depth bounded by -1.0 confirms the isolated subsystem contains disjoint floating islands. Identifying a zero-cut capacity immediately triggers the critical shift from passive diagnostic evaluation to active, automated structural repair. Automated repair is triggered when the remediation flag is enabled and a zero entanglement bottleneck is found. The request is handled either by a cloud commercial AI router or a deterministic local sovereign fallback. Rather than a general suggestion, the router generates a chronologically sorted, mathematically clamped blueprint for the fix. This remediation block details steps to resolve the bottleneck. The applied patch array provides instructions to physically fix the circuit. For example, bridging an ancilla node back to the bulk network restores entanglement. A patch is valid only if it shows a verified improvement status with positive metric deltas. This closed-loop verification ensures that any applied structural fix addresses the physical flaw based on calculated metrics, reducing the need for manual trial and error. Once the patches are delivered, the server moves into the final post-processing phase. The system uses an aggressive garbage collection policy, wiping jobs from RAM 3,600 seconds after they reach a terminal state. This diagram shows how the system handles active computational nodes during a rolling update. Lifespan hooks use a cancel futures command and an asynchrium shield to protect active requests. This allows current pods to terminate gracefully without hanging the ingress controllers. By wrapping physics simulations inside defensive async architectures and strict memory management, the TNQG suite delivers scalable quantum diagnostics without compromising server integrity.